The numbers say the Milky Way should be crawling with life. Hundreds of billions of stars, billions of Earth-sized planets, and more than enough time for someone to get far ahead of you. But the sky is quiet, no clear signals, no obvious alien engineering, just silence. In this video, you're going to see the harsh explanation that the universe may be packed not with neighbours, but with dead Earths, worlds that got oceans, maybe even ecosystems and civilizations, and then failed. And once you see how that happens, the real question becomes whether this Earth can avoid the same fate. You live in a spiral galaxy with on the order of 100 billion to a few hundred billion stars. The Milky Way is about 100,000 light-years across, which is roughly a trillion kilometers, or around 600,000 trillion miles. For a long time, nobody knew how many of those stars had planets. Now that part is basically settled. Planets are normal, not rare. Surveys that use tiny dips in starlight and tiny wobbles in stars have flipped the default assumption. Astronomers talk in simple terms now. For many types of stars, planets per star is around 1 or more. That means when you look at a random star in the sky, the safe bet is that it has planets. Not just a few special systems, almost all of them. A large fraction of those planets are small and rocky, not just gas giants like Jupiter or Saturn. So you're not in a special lucky pocket of the galaxy. You're sitting in a disk of stars where solid planets are mass-produced. Statistically, there are billions of worlds that, at least on paper, sit in the right size range and the right temperature range for liquid water. The galaxy is loaded with potential sites for oceans, atmospheres, and chemistry that could turn into biology. Now add time to that picture, and the tension increases. The Milky Way is roughly 13 billion years old. Earth formed only about 4.5 billion years ago. For the first few billion years here, life was simple. Microbes, single cells. Complex animals with bones and shells and complex bodies only really show up in the last 600 million years. The entire history of human technology, from early tools to radio and rockets, is only a few thousand years, and modern science and electronics are only a few hundred years old. That means there were stars and planets in this galaxy billions of years before Earth even existed. Not just a little earlier, a huge head start. Plenty of those older stars are similar to the Sun and have had time to form rocky planets. If intelligent life can appear on a planet like Earth, there has been time for it to appear on older worlds, develop technology, and then spread. You do not need faster than light travel for that. Even if a civilization built ships that cruised at just a few % of light speed, they could hop from star to star and cross the entire galaxy in tens of millions of years. Compare that to 13 billion years. The timescale to spread is tiny compared to the age of the Milky Way, so if technological civilizations were common, the default expectation is that many of them would already be older than you, more advanced than you, and spread out. But when you look and listen, you don't see or hear them. Radio telescopes have been scanning the sky for decades. They pick up natural signals, pulsars spinning and flashing, the smooth radio glow of neutral hydrogen gas, the faint microwave hiss from the early universe. They do not pick up clear, repeating artificial beacons that stand out from the background as obviously engineered. Optical and infrared surveys map millions of stars and galaxies. They see normal starlight dust, gas galaxy clusters. They do not see obvious gigantic energy structures that would come from a civilization enclosing large numbers of stars and dumping huge amounts of waste heat. So far, starlight spectra look like stars, not like stars wrapped in machines. On all the wavelengths we can currently access, the universe looks natural. It behaves as if there are no long-lived, galaxy-spanning, technological societies waving their arms at us. That mismatch between there was enough time to fill the galaxy and we see nothing obvious is the Fermi Paradox. It's a direct numerical clash. By the numbers, the galaxy should be busy. In observations, it seems empty. One way to reduce that clash is to say very bluntly that most planets fail. Instead of a galaxy full of active, talking civilizations, you get a galaxy full of planets that started on the path and then stopped. Think of Earth-type conditions as a phase, not a permanent state. A rocky planet in the right zone around its star cools, gets oceans, gets an atmosphere with some greenhouse gases, and maybe starts chemistry that leads to life. For a while it's habitable at the surface, but that phase can end. Its star slowly brightens and pushes it toward a runaway greenhouse, or the planet is too small, its core cools, its magnetic field collapses, and the solar wind strips its air, or giant impacts, massive volcanic eruptions, or extreme climate swings push it repeatedly toward the edge until its biosphere cannot recover. Or, later in its history, its own intelligent species destabilizes the climate or triggers global catastrophe faster than the planet can buffer it. From up close, those worlds could have long, complex histories with ecosystems and maybe even industrial phases. From far away, they just look quiet. With your current instruments, a lifeless Earth-sized planet and a never-alive Earth-sized planet both show up as a small dark disk crossing a star, or a faint dot of reflected light. You don't yet see the difference between never started and started, then died. This leads to the dead Earth hypothesis. The idea is that the universe may not be mostly empty of life, it may be mostly past life. The default outcome for many Earth-like planets might be briefly habitable, then dead for good. When you look out at stars, you could be seeing the end state of billions of failed runs. Each run produced a maybe Earth for a while, then something shut it down. You already have strong hints that Earth-class planets can flip from habitable to hostile in your own solar system. Venus is close to Earth in size and mass, but today it is a high-pressure, 460 degrees Celsius hell, about 860 degrees Fahrenheit, with an atmosphere mostly made of carbon dioxide. Mars shows dried riverbeds, lake basins, and minerals that form in long-lasting water, yet now it is a thin-aired frozen desert around minus 60 degrees Celsius, about minus 80 degrees Fahrenheit on average. Both look like worlds that once sat closer to Earth-like and then dropped out of that category. Now scale that up to the rest of the galaxy. Exoplanet surveys show that small rocky planets are common. Many orbit in ranges where surface temperatures could allow liquid water. But being in the right orbit once is not enough. Stars change over time, planet interiors cool, magnetic fields evolve, orbits can shift, climate systems can pass tipping points. When you consider all of that, a long-term stable Earth-like climate starts to look fragile. So you get a harsh picture. The galaxy is very good at building Earth-sized planets and giving them a shot at habitability. It is also very good at ending that habitability through basic physics and chemistry. The quiet sky might not be a sign that life almost never appears. It might be a sign that life appears fairly often, climbs a little way up the ladder, and then gets knocked back down on most worlds. That raises the next key question. If you claim the universe can mass-produce Earths that later die, how do you know it can mass-produce Earths at all? How do you actually know that Earth-like planets are common, not just a guess? Saying maybe there are other Earths used to guesswork. Now it isn't. There is hard data and it points in one direction. Small rocky planets are normal. NASA's Kepler mission is where this really locked in. Kepler stared at one small patch of sky for years, watching more than 150,000 stars at once. It didn't move around, it just sat and measured brightness over and over. Every time a planet crossed in front of its star, the star got a tiny bit dimmer for a few hours or days. That dip was often less than 1%, sometimes just a few hundredths of a percent, but with stable instruments and long observing time, Kepler could see it. From those tiny dips, scientists pulled out thousands of confirmed exoplanets and many more strong candidates. Not just huge gas giants, but planets only a bit bigger than Earth. Some of them orbited their stars in a few days, some took a few hundred days. That second group is important, because orbital periods of a few hundred days usually mean distances from the star, where surface temperatures can sit near the range for liquid water. Roughly Earth-like years and roughly Earth-like energy input. The key result from Kepler is simple. Small rocky worlds are not weird edge cases. They're everywhere in the data. When you sort planets by size, you don't see a giant gap around Earth's radius. You see a lot of planets in that size range, around all kinds of stars at all kinds of distances. Kepler looked at just one narrow cone of the sky and still pulled out thousands. Scale that up to the whole Milky Way, and you're clearly not dealing with a rare type of object. So the next question is obvious. Among all those planets, how many are actually Earth-like in the way that matters for life? Astronomers use a simple term for that, Eta-Earth. It means how many roughly Earth-sized planets in the habitable zone per Sun-like star. Eta-Earth is not an exact number yet, but the current estimates land in a pretty small band, somewhere between about 0.1 and 0.5. Translated into plain language, that means maybe 1 in 10, up to maybe 1 in 2 stars like the Sun has a planet similar in size to Earth, in an orbit where liquid water could sit on the surface. That range comes straight from data. You take the transit signals Kepler saw, correct for the fact that not every planet's orbit lines up just right to transit, add in planets found by the radial velocity technique, where a star's light shifts slightly as an orbiting planet tugs on it, and you build statistics. You ask, given what we can and can't see, how many planets are we missing? Then you run the math. Even if ETA Earth is at the low end, say 0.1, that still means billions of Earth-class or near-Earth-class planets in the Milky Way. If it is at the high end 0.5, you're talking about on the order of 10 billion or more. These are not fantasy numbers. They come from real light curves, real spectra, and real detections, backed by models of how complete our surveys are. But being Earth-sized is not enough. The orbit has to be in the right zone, so the next step is to ask, are good orbits rare, or are they common too? When you plot out the distances of known exoplanets from their stars, you don't just see everything squeezed right up against the star in furnace orbits. Yes, a lot of early detections were hot Jupiters, big planets very close in, because they were the easiest to find. But as sensitivity improved, a broader pattern appeared. Planets are spread over a wide range of orbital distances. In many systems, some sit in regions where stellar heating lines up with the temperature range for liquid water on a rocky surface. That is the habitable zone. The exact location of that zone depends on how bright and how hot the star is. For a Sun-like star, it's around where Earth is, roughly 150 million kilometers from the star, about 93 million miles. For dimmer stars, it's closer in. For brighter ones, it's farther out. Climate and radiative transfer models, the same kind of physics used to predict Earth's climate, let you calculate the inner and outer edges. When you overlay known planet orbits on those zones, you don't see a desert. You see a steady supply of candidates in and near the habitable belt. Some systems even show an almost textbook layout. One inner planet likely too hot, one outer planet likely too cold, and one in the middle sitting in the just right band. The important part is that this is not a single lucky system. It shows up again and again. The habitable zone is not some exotic, rarely occupied ring. It's a region that planets naturally fall into across many systems. Kepler gave you depth on one part of the sky, but most of its stars are hundreds or thousands of light years away. Those systems are too far for close, detailed follow-up of their atmospheres with current telescopes. So the next step was to look for similar planets around nearby stars, where you can actually probe the air they breathe, if they have any. That is where missions like TESS come in. TESS scans almost the entire sky, not just one small patch. It focuses on bright nearby stars, targets within roughly a few hundred light years instead of thousands. The same transit trick applies. Watch for dips in brightness as planets cross in front. Bright, close stars mean those dips are easier to measure with ground-based telescopes and with big space telescopes. On top of that, ground-based observatories add radial velocity measurements. They record tiny shifts in the colour of a star's light as it moves toward and away from us due to a planet's gravity. From that, they estimate the planet's mass. Combine the mass from radial velocity with the size from transits, and you know whether a planet is dense and rocky like Earth, or fluffy like a gas or ice giant. The result of this combined effort is a growing list of nearby rocky planets in or near their stars' habitable zones. Every year, that list gets longer. These are not vague ideas, they are specific targets with measured sizes, orbits, and often masses. They are close enough that current and upcoming telescopes can try to detect molecules in their atmospheres, water vapor, carbon dioxide, maybe even oxygen or methane, in precise units like parts per million. So now step back and connect this to the bigger question. You know, small rocky planets are common. You know, habitable zone orbits are not rare. You know that in the Milky Way alone, the best estimate is billions of Earth-size, roughly Earth temperature worlds. On Earth, life appears in the record fairly quickly after the planet cooled enough for oceans to form, on the order of a few 100 million years. The galaxy is more than 10 billion years older than that timescale. On paper, this combination, huge numbers of Earth-like planets, plenty of time, plus the fact that life here did not take forever to start, points toward a universe that should be rich in biospheres and, at least in some cases, rich in technological civilizations. Yet when you actually listen with radio telescopes and look with infrared and optical surveys, you hit that same brick wall of silence. The more solid the numbers on Earth-like planets become, the worse that silence looks. The universe is clearly set up to mass-produce Earth-class worlds, but it does not show clear signs of mass-produced long-lived civilizations. That gap is your warning. Earth-like in size and temperature does not mean safe or stable over billions of years. It just means eligible to try. The next step is to ask how that eligibility changes with time. Stars do not stay the same brightness forever. Habitable zones move, planet climates shift. The question is not just how many Earths can form, it's how long do they stay habitable before physics turns them into dead Earths. You probably think the habitable zone around a star is like a fixed ring in space. Once a planet sits in it, it stays good forever. That picture is wrong. The ring moves, and it moves because stars change. The sun is not a stable light bulb. It is a nuclear reactor. Deep in its core, hydrogen fuses into helium. As that helium builds up, the core slowly contracts and heats, and the outer layers respond. The end result is simple to state. The sun gets brighter with age by roughly 10% every billion years. That number doesn't come from a guess. It comes from models of stellar structure that are checked against real star clusters, where you can see stars of known ages and compare their brightness, and from details like the sun's internal vibrations and neutrino output. Run that trend backward in time and you hit the faint young sun paradox. Around 4 billion years ago, the sun should have been maybe 20 to 30% dimmer than it is today. With that little energy, simple physics says Earth should have been frozen solid with global ice oceans, but the rocks disagree. Ancient sedimentary layers and certain isotopes show liquid water on the surface back then. So early Earth had a weaker sun but somehow stayed warm enough, probably thanks to a stronger greenhouse effect from higher carbon dioxide and methane. Run the trend forward instead, and the story flips. The sun keeps turning up the heat, and eventually that extra energy overwhelms the Earth's ability to stay in a comfortable state. Long before the sun becomes a red giant, its normal, slow brightening is enough to bake the planet. So if the star is changing, what happens to this so-called habitable zone around it? By definition, the classical habitable zone is the range of distances where a planet with an Earth-like atmosphere can keep liquid water on its surface. That zone depends mainly on how much energy the star is putting out. If the star brightens, the whole zone shifts outward. Climate models that plug in realistic oceans, clouds, and gases show that Earth itself will not sit comfortably in the centre of that zone forever. As the sun's luminosity creeps up, Earth gets closer to the inner edge. The timescale is not remote science fiction. The best estimates say that in roughly 1 to 2 billion years, increased solar output will push Earth out of the truly safe region. You don't need the red giant phase where the sun swells to many times its current size. A modest increase in brightness is enough to raise evaporation rates, change cloud cover, and start driving the climate toward a moist greenhouse state, where the upper atmosphere fills with water vapor. Keep going and you can hit a full runaway greenhouse, where the planet locks into a much hotter state. For most sun-like stars, this is normal evolution. Their habitable zones are not fixed shells. They slide outward over time. If the habitable zone is sliding, that means no Earth-like world gets a permanent pass. Each one gets a window. Too early in a system's history, when the star is faint, the habitable zone sits closer in. A planet at Earth's current distance would be a snowball, maybe with liquid water only under ice or near volcanoes. Too late, after the star has brightened enough, the same orbit is too hot. Surface water boils off, or the climate flips into some other extreme. The comfortable middle is a band in time as well as space. Earth's own timeline shows how tight this can be. Life here shows up in the record fairly early, within a few 100 million years of the oceans forming. But for most of Earth's 4.5 billion year history, life is simple. Single-celled organisms and microbial mats. Complex multicellular animals, with organs and nervous systems, are mostly a story of the last 600 million years or so. Land plants and land animals with large complex bodies are only in the last 10 to 15% of Earth's duration so far. Intelligence capable of radio telescopes is in the last sliver, less than 1%. That tells you something important. It can take billions of years for a planet to go from liquid water and microbes to brains and technology. If the habitable window is too short, if the star brightens faster, or the climate system is less stable, there might not be enough time. The planet could either stay frozen for too long or hit runaway heating too early. In both cases, you end up with a world that had a surface ocean and chemistry, maybe even simple life, but never gets to the point of complex, thinking organisms. So what actually pushes a planet over the edge from just hotter to runaway greenhouse? Climate models let you test this by turning up the incoming starlight in small steps. Add only a few % more energy at the top of Earth's atmosphere, in a model that includes oceans and realistic cloud physics, and you see water vapour in the upper atmosphere start to climb. Water vapour is a strong greenhouse gas. The more of it you put high in the air, the more heat you trap. High-altitude water also runs into strong ultraviolet light from the star. Those UV photons break water molecules apart. The hydrogen is light and can escape to space, while the oxygen tends to stay behind, either as gas or locked into rocks. Over tens to hundreds of millions of years, this process lets a planet steadily lose its oceans from the top down. All the while, more evaporation means more water vapour, which means more heating, which means more evaporation. At some point, the system crosses a tipping point. Beyond that, no normal weathering or carbon cycle feedback can pull it back to a cooler state. The planet jumps to a new equilibrium with a much hotter surface, a thick greenhouse atmosphere, and little or no liquid water. That is the pathway scientists think Venus likely followed. Now put this into a galactic context instead of just one solar system. The Sun is about 4.6 billion years old. Many Sun-like stars in the Milky Way are older, 5, 7, even 9 or more billion years old. Because they are older, they are also brighter now than the young Sun was at the same mass. Any Earth-like planets that started off near the inner part of their original habitable zones around those stars have lived with increasing heat for billions of years. Some of them will have already crossed their inner edges. Their oceans, if they had them, are gone or greatly reduced. Their atmospheres have been reshaped. Their surfaces have been sterilized or pushed into extreme states. You can also have the opposite problem. Planets that started near the outer edge might have spent a long time too cold, only entering a good temperature band late, when there was less time left before the star's brightening pushed things too far. In both directions, the window narrows. Multiply that across hundreds of billions of stars, and a pattern appears. Even if many systems start with an Earth-class planet in a promising orbit, the relentless brightening of stars will, one by one, push those planets out of comfort. If you could watch the galaxy and fast forward, you would see zones of habitability drift outward like moving bands, leaving behind worlds that were once mild and are now baked, or otherwise altered. From tens or hundreds of light years away, those planets don't announce what happened. They just show up in your telescope as small Earth-sized objects in the wrong climate state. Dry, hot, or otherwise hostile. Dead Earths by default. But stellar brightening is only one way to kill an Earth-like world. Some planets never even make it to the end of their window because of what happens inside their own atmosphere and interior. And the clearest examples of that failure are orbiting the same star you do, waiting to be studied. How can two planets so similar on paper end up as totally different worlds in reality? Venus is your clearest answer, and it is not a pleasant one. Venus is almost a twin of Earth in basic stats. Its diameter is about 12,100 kilometers, Earth's is about 12,700. Its mass is about 80% of Earth's. Surface gravity is only a little lower than what you feel right now. It orbits the Sun at about 108 million kilometers, while Earth sits at about 150 million kilometers, so it's only about 30% closer in. If you just read those numbers in a table, you would expect slightly warmer Earth as the description. Instead, the surface of Venus sits at around 460 degrees Celsius, roughly 860 degrees Fahrenheit, under an atmosphere about 90 times thicker than Earth's. That's like taking the pressure you feel at sea level and multiplying it by 90, similar to being almost a kilometre, about 3,000 feet underwater. The air is mostly carbon dioxide with clouds of sulfuric acid. Probes that land there survive for minutes to a couple of hours before the heat and the pressure destroy their electronics and crush their structures. This is what a completed runaway greenhouse looks like. Stable, but in a permanently lethal state. So here is the key question. Was Venus always this bad? Or did it become this way over time? Multiple lines of data say it changed. One of the strongest clues is in its hydrogen. Not all hydrogen atoms are the same. Some are slightly heavier because they have an extra neutron. That heavier version is called deuterium. Measurements of Venus's atmosphere show a much higher ratio of deuterium to normal hydrogen than Earth has. That is exactly what you expect if Venus once had a lot more water. And over time, the lighter hydrogen escaped to space faster, leaving the heavier deuterium behind. It's like a fingerprint of long-term water loss. Climate and interior models back this up. If you take a young sun that is a bit dimmer than today, and you give Venus an initial water inventory similar to Earth's, you can find scenarios where liquid oceans are stable on its surface for hundreds of millions, maybe even 1 billion or more years. The exact duration depends on details. How fast the young sun brightened, how thick the early atmosphere was, how active volcanism was. But in many of those simulations, Venus starts as a genuine ocean world, not that different from early Earth. The horror story is not that Venus was always a furnace. The horror story is that it might have been habitable for a long time and then left that state and never went back. So what actually flips a planet like that from wet and warm to dry and burning? The trigger is simple enough in physics terms. Take a planet with surface water and some greenhouse gases in the air, increase the incoming sunlight. As the surface warms, evaporation ramps up. More water vapor goes into the atmosphere. Water vapor itself is a powerful greenhouse gas, so it traps more heat. More heat drives more evaporation. You get a positive feedback loop. Extra warmth makes more vapor makes more warmth. On a planet at Earth's distance, that loop strengthens the greenhouse effect but doesn't normally run away. On Venus, about 30% closer to the Sun, you start with more incoming energy per square meter. As the young Sun brightened, there was a point where that feedback likely crossed a critical threshold. Once past that point, no reasonable rock weathering or carbon cycle processes could remove greenhouse gases fast enough to stabilize the temperature again. The sequence looks like this. The oceans warm and begin to boil off. The upper atmosphere gets wetter. Ultraviolet light from the sun breaks apart water molecules. Hydrogen escapes to space. Oxygen reacts with surface rocks or ends up in the atmosphere for a while. As water is lost, what's left behind is an atmosphere increasingly dominated by carbon dioxide, coming from volcanoes and from rocks that release CO2 when heated. That CO2 adds even more greenhouse effect. The planet moves toward a new balance point. Thick CO2 atmosphere, no surface oceans, extremely high surface temperature. That is the Venus route. Once a planet gets into that state, what stops it from changing back? On Earth, the long-term climate is stabilized by plate tectonics, oceans, and the carbon silicate cycle. CO2 comes out of volcanoes, dissolves in rainwater, reacts with rocks, and ends up as carbonates on the seafloor. Tectonic plates drag those rocks down, melt them, and eventually release some CO2 again. Water is central in that loop. Venus appears to be missing some of that machinery now. With no liquid oceans, you lose the main solvent for weathering. Without efficient weathering and with little or no plate tectonics in the Earth sense, there is no strong sink to pull CO2 out of the atmosphere over long timescales. At the same time, the interior of Venus is still hot. It's still out gases. Radar mapping from orbit shows huge lava plains and signs of massive volcanic resurfacing in the past. The surface seems to have been reset geologically on large scales, but there are no river systems, no clear signs of long-lived surface water flows in the current terrain. So once Venus dried out, its climate likely got locked into a near irreversible configuration. Dense CO2, crushing pressure, extreme heat. There is no obvious natural route back to a cool, wet state. That makes Venus more than just an odd neighbour. It is proof that an Earth-sized rocky planet at a not insane distance from a sun-like star can spend some time in the habitable window and then snap into a dead, hellish state for good. Now take that template and go back out to the galaxy. When astronomers look at exoplanet data, they see a lot of planets that are slightly larger than Earth, orbiting closer to their stars than Earth does to the Sun. Many of those orbits are right around or just inside the inner edge of the habitable zone for their particular star. Those planets are often called super-Earths or mini-Neptunes based on their sizes and densities, but for a big fraction of them, the likely reality is exo-Venus, a rocky world with a very thick, hot atmosphere. Telescopes that can take spectra of their atmospheres during transits already see hints that some of these worlds have high temperatures and cloudy, opaque skies. As instruments improve, scientists are starting to separate warm, potentially water-bearing atmospheres from those that are probably hot and CO2 choked. Every time a close-in rocky planet turns out to be wrapped in a thick, hot atmosphere, it fits into the Venus pattern. Inner zone planets that slid past a tipping point and never came back. If the inner parts of habitable zones around many stars are full of exo-Venuses, that means something important. It means a big fraction of Earth-sized planets in the right general area are not mild ocean worlds. They are planets that either never had surface water for very long, or had it and lost it in a runaway. They are already dead Earths, or Earths that only briefly counted as alive before their climate crossed the line. And if one side of Earth's orbit gives you a dead, overheated twin, what happens on the other side of the Sun, where the light is weaker and the problem is not too much heat but too little? Mars shows you the opposite failure mode from Venus. Same star, same neighbourhood, completely different way to kill a world. Right now, Mars is a cold, dry desert. The average surface temperature is about minus 60 degrees Celsius, around minus 80 degrees Fahrenheit. At the equator on a warm afternoon it can creep above freezing, but at night it drops sharply. The air pressure at the surface is less than 1% of Earth's sea level pressure, about what you'd feel near the edge of space in a high-altitude aircraft. Under those conditions, liquid water on the surface is basically impossible. It either boils away or freezes in minutes. You'd need a pressure suit and a heated habitat just to stand there for more than a few seconds. But when orbiters and rovers send back images, the landscape doesn't look like a place that has always been dry. It is full of dried-up river valleys, branching like tree limbs that run for hundreds of kilometers. You see delta fans where water once slowed down and dropped sediment. You see layered deposits and craters that look exactly like lake beds. Geologically, Mars is loud and clear. I used to be wet. The minerals back that up. Certain clays only form in the presence of liquid water over long periods. Some sulfates point to evaporating lakes and seas. NASA's rovers, like Curiosity and Perseverance, have drilled into rocks and found fine layers laid down by calm water, not brief floods. These are not signs of a one-time splash. They are signs of water that stuck around. Orbiter data takes it further. High-resolution cameras show features that look like ancient shorelines along the edges of Mars's northern lowlands. The topography suggests that long ago, much of the northern hemisphere may have held an ocean. Radar instruments see thick deposits of ice buried under dust and rock, not just at the poles but in mid-latitudes. Neutron spectrometers, which respond to hydrogen in the ground, show that large parts of the subsurface hide frozen water. Put this together, and early Mars stops being a red desert in your mind. It turns into a planet with rivers, lakes that lasted thousands to millions of years, and maybe a cold, shallow ocean in the north. In some regions, for long stretches of time, it would have looked and felt much more like parts of Earth than like the Mars you see today. That is a genuine habitable phase. So what stripped that habitability away? Mars is only about half of Earth's diameter and about 1/10 of Earth's mass. That means its gravity is weaker, about 38% of Earth's surface gravity. More importantly for long-term habitability, it has a smaller core that cools faster. At some point in its history, Mars had a global magnetic field, generated by motion in its liquid core, the same basic dynamo process that gives Earth its magnetic field. That field acts like a shield, deflecting charged particles from the Sun. Over time, Mars's core cooled and the dynamo died. The magnetic field weakened, then collapsed. Once that happened, the upper atmosphere was exposed directly to the solar wind. A constant stream of high-energy particles flowing out from the Sun at hundreds of kilometers per second, hundreds of thousands of miles per hour. Those particles can slam into atmospheric molecules, knock them around, and help them escape to space. Spacecraft like NASA's MAVEN mission have actually measured this process. They see ions, charged atoms and molecules flowing away from Mars, carried off by the solar wind. This is not just a theory from the deep past, it is still happening today, slowly but constantly. Over hundreds of millions to billions of years, that kind of erosion thins the atmosphere dramatically. As the atmosphere thinned, surface pressure dropped. With lower pressure, water becomes harder to keep liquid. It boils at lower temperatures. At the same time, a thinner atmosphere holds less heat. The greenhouse effect weakens and the planet cools. Without a thick blanket of air, Mars also loses heat quickly at night. The climate swings get harsher. Regions that once had rain or snow-feeding rivers turn into polar-style deserts. Water that had been liquid on the surface has two main options: freeze or escape. Some of it froze into the ground as permafrost and into the polar caps as layered ice. Some of it, especially hydrogen from water molecules broken apart by sunlight, escaped to space. Over long timescales, Mars shifted from blue and brown to brown and red, and finally to the dusty red we see today. The famous red colour comes from iron minerals in the rocks that have been oxidized, basically rusted, over time. Dust storms lift that fine red material into the air and spread it across the planet. Under that thin layer of dust, though, is a more serious message. This world went through a habitable phase and then froze out of it. If any life started in those ancient lakes and rivers, it was hit by a moving target. The surface environment that may have been friendly for millions of years slowly became lethal. Could anything have survived? If simple life did appear on early Mars, its best chance would be to retreat underground, into rock pores or buried aquifers, where liquid water might still briefly exist, warmed by internal heat. Protected from radiation and extreme surface temperature swings, microbes could in theory hang on for long periods, but that is a very different story from a planet with open seas and a thick sky. From orbit from another star system, today's Mars is just a cold, quiet rock with a thin atmosphere. Its active, wet past is not obvious. Now zoom back out to the inner solar system and look at the pattern. You have three roughly Earth-class terrestrial planets in a row: Venus, Earth, Mars. Venus is almost Earth's twin in size, but ran into a runaway greenhouse and became a 460°C pressure cooker. Mars is smaller, once wet, but lost its magnetic field, lost most of its atmosphere, and froze into a -60°C desert with air so thin water cannot stay liquid. Earth is in the middle, both in distance and in outcome. It has kept a thick, breathable atmosphere, liquid oceans, and a temperature range where complex life can survive at the surface. Venus and Mars both likely had long periods with stable surface water. Venus may have had oceans for hundreds of millions of years or more before overheating. Mars had rivers and lakes for similar or longer spans before its atmosphere dwindled. Both of them ended up hostile to surface life as their internal and external conditions changed. Both sit as end states, one burned, one frozen. Earth is the outlier that threaded the needle so far. It kept a strong magnetic field. It kept plate tectonics and a working carbon cycle. Its orbit and mass gave it a wide enough window for complex life to evolve before the sun's brightening pushes it too far. When you line the three up, the message is not, Earth-like worlds are safe. The message is, out of 3 local tries, 2 failed. Scale that up to the galaxy. If many stars form inner rocky planets like Venus and Mars, plus mid-zone planets like Earth, then for every long-lived stable Earth you can expect a lot of almosts. Planets that were wet and mild for a while, then drifted out of habitability as their cores cooled or their stars brightened. From light years away, today they just look like small planets with thin or thick atmospheres in the wrong climate state. They are Mars-like dead Earths, frozen mid-story. And even on a planet that does manage to stay in the right zone, like Earth, the danger is not over. Keeping liquid water and a thick atmosphere doesn't guarantee stable, gentle conditions for life. The fossil record shows that even here, complex life has been nearly erased more than once. So the next question is not just, can a planet stay habitable? It's, once life takes hold, how often does the planet itself almost wipe it out? You already know Earth is dangerous from orbit. Venus burned, Mars froze. But if you really want to see how close this planet came to joining them, you'll have to look down into the rocks. The fossil record is not a calm story of steady progress. It looks more like a crime scene. In the last 500 million years, paleontologists see at least 5 major mass extinctions. They have long names: Ordovician to Silurian, Late Devonian, Permian to Triassic, Triassic to Jurassic, Cretaceous to Paleogene, but the pattern is simple. Each time, more than half of all species vanish in what geologically is a short burst. In the worst one, at the end of the Permian period about 252 million years ago, over 90% of marine species and around 70% of land vertebrate species disappear. Almost everything dies. You go from complex, diverse ecosystems to a stripped-down world where a few hardy survivors have to rebuild from near zero. You might think events that big must always come from space, from something clearly not Earth. One of them definitely did. The most famous extinction is the one that ended the age of the non-avian dinosaurs, 66 million years ago. The evidence points to a single brutal trigger, a roughly 10-kilometre asteroid, about 6 miles across, slamming into what is now the Yucatan Peninsula in Mexico. It hit at something like 20 kilometers per second, tens of thousands of miles per hour. The energy release was equivalent to billions of nuclear bombs going off at once. That impact gouged out the Chicxulub crater, about 180 kilometers, around 110 miles, wide. It blasted rock and sulfur-rich dust high into the atmosphere. That dust blocked sunlight worldwide. Photosynthesis stalled. Food chains collapsed. Global temperatures dropped for years, then swung back as greenhouse gases from fires and vaporized rock kicked in. You see a thin layer of iridium-rich material spread around the world in rocks of the same age, and tiny grains of shocked quartz that only form under extreme pressures like nuclear tests or asteroid hits. Small changes in angle, speed, or timing would have changed everything. Maybe the asteroid misses, maybe it hits deeper ocean, and the effects are different. Maybe dinosaurs never die out, and mammals stay small and marginal. The point is not poor dinosaurs. The point is that a single random rock in the right orbit can reboot an entire planet's evolutionary path. But not all the big kill events needed something from outside. Sometimes the planet does it to itself. The end Permian extinction, the worst one, lines up with colossal volcanic eruptions in what is now Siberia. For hundreds of thousands of years, huge volumes of lava poured out over an area larger than the United States. That kind of activity vents enormous amounts of carbon dioxide and methane into the atmosphere. Greenhouse gas levels spike, global temperatures rise fast on geological timescales. Warm water holds less oxygen, so the oceans start to run low on it. In the rocks from that time, you see black shales that form in oxygen-poor water, big swings in carbon isotopes that match massive carbon release, and a fossil record that crashes. Coral reefs die. Many shell-forming animals disappear. On land, forests burn and vanish. You don't need a comet or aliens to explain this. You just need a geologically active planet that happens to run a supervolcano event in the wrong place, over the wrong timescale. In effect, Earth poisoned its own oceans and atmosphere. And sometimes the direction flips. Instead of too much heat, you get too much cold far beyond normal ice ages. Earlier in Earth's history, there were Snowball Earth episodes where ice sheets may have reached nearly to the equator. You find glacial deposits, rocks and sediments left by ice, sitting in what were tropical latitudes at the time. On top of those layers, you see cap carbonates, thick carbonate rocks that seem to have formed quickly as the planet thawed. The simplest reading is dramatic. Earth froze over almost completely, stayed that way for a long time, then snapped back into a warm state. On a snowball Earth, most of the ocean surface is sealed under thick ice. Sunlight can't penetrate far. Photosynthesis in the surface ocean collapses. The only comfortable places left might be near volcanoes, in thin cracks in the ice where liquid water meets light, or deep in the subsurface. Life has to survive in scattered refuges, while the planet sits in a kind of deep freeze. Then, as volcanoes keep pumping out CO2, and there are no normal weathering processes on ice-covered continents to pull it down, greenhouse gases build up to huge levels. Eventually, the greenhouse effect overwhelms the high reflectivity of the ice. The planet warms rapidly. Ice melts. You jump from global slush to hot, high CO2 conditions. The same feedbacks that can stabilize climate can also push it between extreme states if the inputs change enough. When you stack all of this together, asteroid strikes, supervolcanic eruptions, near global glaciations, Earth stops looking like a gentle cradle and starts looking like a tightrope walk. Asteroid impacts big enough to disrupt climate are rare on human timescales, but not on hundreds of millions of years. Massive volcanic provinces don't pop up every century, but they do happen in the long run. Snowball episodes are separated by long stretches, but they show up in the rock record more than once. These are recurring patterns, not freak one-off accidents. Complex life on this planet survived because of a mix of factors: sheer luck in impact timing and size, the buffering effect of deep oceans and a thick atmosphere, and biological resilience. After each crash, evolution slowly refilled the empty niches, but often with entirely different groups of organisms. There is no law that says that had to succeed every time. If one asteroid had been a bit larger, if one burst of volcanism had lasted longer, if one snowball period had gone a bit colder, complex life might not have come back at all. From far away, a failed recovery just looks like a planet with strange rock chemistry and simple or no life on the surface. It doesn't advertise the fact that it once had forests, coral reefs, or intelligent species. The evidence for those can be erased over tens or hundreds of millions of years. So even on a world that sits in the right zone around its star with the right size and the right atmosphere, the story is not smooth progress from microbes to technology. It's a series of close calls. Mass extinctions, climate swings, and global disasters keep trying to push the biosphere off the cliff. This planet made it through at least 5 major hits in the last 500 million years alone. If that's what survival looks like on one of the lucky Earths, you have to ask the next question. What happens on all the less lucky ones? And what happens when you add in dangers that don't just come from inside the solar system but from deep space itself? Stars themselves are another threat. They don't just warm planets. Some of them end as weapons that can reset or erase whole biospheres in an instant. Massive stars, many times the mass of the Sun, live fast and die as supernovas. When they blow, for a few weeks they can outshine an entire galaxy. We've seen thousands in distant galaxies, and in our own we see the leftovers, expanding gas clouds like the Crab Nebula, the wreckage of a star that exploded in the year 1054. That brightness isn't just pretty, it comes with a flood of high-energy photons and a blast of charged particles, cosmic rays, ripping through nearby space. If a supernova goes off close enough to a habitable planet, the radiation doesn't just light up the sky, it hits the atmosphere hard. Atmospheric chemistry models show that a blast within a few tens of light years can damage or partly destroy the ozone layer. Ozone is the thin shield high in the atmosphere that blocks most of the sun's ultraviolet radiation. Strip a big chunk of it away, and suddenly the surface gets hammered by UV, DNA damage spikes. Food webs that depend on surface or near-surface organisms start to fail. The chemistry chaos can last thousands of years, not just days, before the ozone layer fully recovers. That's one way to sterilize large fractions of a planet's surface without ever touching the ground. Nothing needs to physically hit the planet. The star explodes, the radiation slams into the atmosphere, and the biology takes the hit. And supernovas aren't the worst thing out there. Gamma-ray bursts, or GRBs, are on another level. They are short flashes, sometimes only fractions of a second to a few minutes long, but they emit more gamma-ray energy in that instant than a normal star like the Sun will emit in its entire 10 billion year life. Satellites in Earth orbit detect them all over the sky, many from galaxies billions of light years away. The leading models say they come from very massive stars collapsing into black holes, or from neutron stars merging. The key detail is that GRBs are beamed. They shoot out narrow jets of energy, more like a focused beam than a light bulb. If your planet sits inside that beam, even from a few thousand light years away, the energy per square meter at the top of the atmosphere can be devastating. Models suggest a strong GRB pointed at Earth from that kind of distance could strip away a large part of the ozone layer in minutes. Again, the result is a long-lasting rise in surface UV from your own star. The gamma rays themselves do the initial damage. The follow-up UV finishes the job on exposed life. Unlike an asteroid impact, a GRB doesn't leave a neat crater you can point to. In the rock record, it would show up at best as a sudden shift in certain isotopes, changes in nitrogen compounds, or a strange extinction pattern that doesn't match impacts or volcanism, that makes GRBs good candidates for invisible mass extinction triggers. Some researchers have proposed that at least one of Earth's past die-offs could have been helped along by a GRB or a very close intense supernova. The next step is to ask where in the galaxy these events are most common. Supernovas and long GRBs tend to come from very massive, short-lived stars. Those stars don't live for billions of years like the Sun. They burn out in a few million years. You find them where stars are being born actively, in dense spiral arms, near the galactic center, and in starburst regions. When you simulate the Milky Way and plot where massive stars explode over time, you get a danger map. Inner regions and arms with higher rates of lethal events, outer regions and quieter patches with lower rates. The Sun does not live in the worst parts of that map. It orbits in the galactic disk, but not too close to the center, and not in a crazy star-forming region. People often call it a galactic suburb for that reason. It still sees supernovas, but not at the highest possible frequency. There is no guarantee that an Earth-like planet ends up in such a mild location. Place a similar planet closer to the center or deep in a crowded spiral arm, and it will experience more nearby explosions over billions of years. That matters because supernovas and GRBs don't need to be constant to be effective. A single event in the wrong place and time can cut down complex life brutally. If these events are more common in certain galactic zones, then large chunks of the galaxy are simply worse places for long-term surface habitability. They don't stop planets from forming. They don't stop life from starting. They just keep resetting the clock. On Earth, tracing a past GRB would be hard. Unlike Chicxulub, there's no impact basin. Unlike the Siberian traps, there's no giant basalt province. You might see an extinction that looks odd compared to volcanism and impacts, plus chemical hints of a burst of atmospheric ionization. But after tens or hundreds of millions of years, those details get blurred. From the outside, the pattern is simple. Ecosystems grow for a few 100 million years, then a sudden external radiation hit knocks them down. Deep-sea microbes and underground life might survive. Complex surface life, including any technology that depends on stable agriculture and climate, takes the main blow. So now your threat list looks like this. Internal disasters like volcanism and snowball Earth, random bullets from within your solar system like asteroids, and external shots from the galaxy itself, supernovas and GRBs. Planetary systems orbit through a disk filled with massive stars about to explode, tight binaries heading for mergers, and active regions around black holes. Over billions of years, any given system passes through higher and lower risk zones. From this angle, the universe is not a passive stage where planets quietly evolve life. It is an active, sometimes hostile environment. An Earth-like planet is not just a rocky sphere at the right distance from its star. It is a target that has to survive repeated hits from inside and outside. The longer it exists, the higher the chance that one of these shots lands close enough and strong enough to wipe its surface clean. If you combine all of this with the fragile climate windows and mass extinctions you already saw, a pattern is forming. It's not enough for a planet to be built correctly. It has to dodge geologic disasters, orbital quirks, asteroid impacts, and galactic radiation bursts for billions of years, while life slowly climbs toward complexity and intelligence. This is exactly the kind of grinding, multi-level danger that can turn a galaxy full of potentially habitable worlds into a galaxy full of dead or never quite made it Earths. Which leads to the next problem. Maybe the real killers aren't just single events, but a whole sequence of extremely hard steps that most planets never clear. You've seen a long list of ways planets and biospheres can fail. But even if a world dodges all the obvious bullets, there's another problem. Some steps on the path to a spacefaring civilization might be so hard that almost nobody gets through them. That's the idea behind great filters. A great filter is any step in the journey from a sterile rock to a galaxy-shaping civilization that almost always stops the process. It can sit early, before life starts. It can sit in the middle, between microbes and complex animals. Or it can sit late, between a young technological society and a mature, long-lived one. Wherever it is, it turns lots of habitable planets into almost no planets with civilizations that last and spread. From the outside, that looks like a galaxy full of Earth-like rocks that never wake up, or that wake up briefly and then go dark again. To see where those filters might be, look at Earth's own timeline in detail. Earth formed about 4.5 billion years ago. Within a few 100 million years of the surface cooling and oceans forming, you already see signs of life, chemical signatures and microfossils in rocks more than 3.5 billion years old. So the jump from oceans plus basic chemistry to simple cells might not be especially hard, at least under Earth-like conditions. It happened quickly in geological terms, but then the story slows down. For billions of years, Earth is basically a microbial planet. Simple single-celled organisms dominate the oceans. Cells with complex internal structures, eukaryotes with nuclei and organelles, take more than 1 billion years to show up clearly in the record. Multicellular animals with shells and skeletons only explode into diversity in the last 540 million years or so, during and after the Cambrian period. Complex land plants and big land animals show up even later. Intelligence capable of science and technology is newer still. Homo sapiens is maybe 300,000 years old. Agriculture is around 10,000 years old. Industrial technology is a few hundred years old. On a 4.5 billion year timeline, your entire civilization slice is a hairline crack at the end. That pattern hints that some of the biological steps are extremely slow, fragile, or dependent on rare combinations of events. Maybe going from simple cells to complex eukaryotic cells is a great filter. Maybe the jump to multicellular life that can build brains is a filter. Maybe big brains themselves with the right social behaviour to use tools and language are highly unlikely. For most of Earth's history, nothing with our level of intelligence existed, even though the planet had oceans and continents the whole time. Then there are the non-biological filters, the planetary hardware. Earth has long-term plate tectonics. Its outer shell is broken into plates that move a few centimetres per year, a couple of inches per year, driven by mantle convection. That motion drags oceanic crust down into the mantle at subduction zones and brings fresh rock up at mid-ocean ridges. Tectonics and erosion work together with water and CO2 to run the carbon silicate cycle, a slow thermostat that helps stabilise climate over tens to hundreds of millions of years. Earth also has a strong magnetic field, generated by a still liquid convecting iron core. That field extends tens of thousands of kilometres into space, forming a magnetosphere that deflects a lot of the solar wind. It stops the atmosphere from being directly sandblasted away by charged particles, the way Mars's atmosphere was. Mars shows what happens when at least one of these systems fails. Its smaller core cooled, its dynamo shut down, its field collapsed, and the solar wind started stripping its air. Venus shows another path. If tectonics and water-driven weathering don't work like they do here, CO2 can build up and never get pulled back down into rocks, driving a runaway greenhouse. Many exoplanets may hit similar physical walls. Some are too small to keep a hot, moving core for their billions of years. Some are tidally locked around red dwarf stars, with one side baking and one side freezing, which may disrupt plate tectonics and magnetic dynamos. Others may start with so much water or so little land area that the carbon silicate thermostat never kicks in properly. For those worlds, the great filter is not biology. It's geology and magnetism. They might get a brief habitable phase, then slide slowly but irreversibly into atmospheric loss, deep freeze, or permanent steam world. Even if a planet passes the right hardware tests and life there climbs all the way up to intelligence, the filters don't stop. Intelligence doesn't guarantee survival. A species can invent tools, language, agriculture, cities and industry, and still fail to build a stable, long-lived civilization. The weak points here are social and technological. Does that civilization manage its resources, or does it burn through them in a few centuries? Does it avoid full-scale nuclear war? Does it handle fast climate change that it causes itself, or does it drive its own biosphere into collapse? Does it deploy powerful technologies like advanced biotech or AI without creating new, uncontrollable failure modes? From space a million years later, a civilization that failed those tests just looks like a slightly altered planet. You might see hints of past industry locked into certain rock layers, unusual concentrations of metals, plastics turned into strange organic remnants, isotope patterns from fossil fuel burning, but there is no bright radio beacon, no megastructure, nothing easy to spot. The technosphere appears, flares for a few thousand years, and then disappears. The planet joins the list of worlds that almost made it. Put all of this together and the path from rock to radio starts to look like a chain of narrow gates. First, a star and disk have to form in the right place in the galaxy, with enough heavy elements. Then a rocky planet has to form in the right orbital range. That planet has to keep its atmosphere, avoid being sterilized by giant impacts or stellar flares, and cool into a stable state with liquid water. Life has to start. It has to survive early disasters and evolve complexity. It has to get eukaryotic cells, multicellular bodies, nervous systems, big brains. A technological species has to appear. That species has to build a civilization that can ride out internal and external shocks without collapsing. Finally, that civilization has to spread and last long enough to become obvious across interstellar distances. Each stage is a possible great filter. The fact that you see so many Earth-like planets but no clear signs of long-lived galaxy-spanning civilizations suggests there isn't just one filter. There are several. Most planets probably fail at one of the early or middle steps, no life or only microbes forever, or repeated mass extinctions that never quite lead to intelligence. Some planets get intelligence but fail the late filters. They don't manage their own power. From far away, all of those failures look similar. A rocky planet in or near a habitable zone, with maybe some odd chemistry but no loud technosignatures. A dead Earth or a never-awakened Earth. The Great Filter idea explains how a universe that clearly knows how to build Earth-class planets can still present you with a silent sky. But there's another twist. Even on a planet that gets through many of these gates, long-term survival depends on one more factor: how stable its climate really is. And the more you study climate physics, on Earth and on exoplanets, the more it looks like stable, gentle conditions are not the norm. They're the exception. So the next question is simple and uncomfortable. If climate itself is a knife edge, how many Earth-like planets ever manage to balance on it for long? Earth's climate looks calm on human timescales, but in deep time it's a tight control system fighting to keep you out of the ditch. The fact that it's worked for more than 4 billion years is not normal. It's weird. On very long timescales, Earth has something like a thermostat, the carbon silicate cycle. Volcanoes push carbon dioxide into the atmosphere from deep inside the planet. That CO2 dissolves in rain, makes weak carbonic acid, and that rain attacks rocks on continents. Weathering products wash into the ocean, where carbon gets locked into minerals like carbonates on the seafloor. Plate tectonics drag some of that carbon-rich rock back into the mantle, where it can eventually melt and come out again in new volcanic eruptions. Temperature changes how fast this loop runs. Warmer climates usually mean more rainfall and faster chemical weathering, which pulls CO2 out of the air faster and cools things back down. Cooler climates slow weathering, letting volcanic CO2 build up and warm the planet. Over millions to tens of millions of years, this acts as a rough stabilizer. Geological and isotope data say that despite huge swings, Earth has managed to keep liquid oceans almost continuously for more than 4 billion years. That is not something you automatically get just because you have rock and water. It's a sign that a whole set of deep processes happen to line up here. The faint young sun paradox is one of the clearest tests of this. Early in Earth's history, around 4 billion years ago, the sun was about 20 to 30% dimmer than it is today. If you keep Earth's current atmosphere and just turn down the sun by that much, global average temperature drops well below freezing. You should get a planet covered in ice from pole to equator. But when you look at very old rocks, you find sedimentary layers that only form in liquid water, and isotopic signatures that fit a relatively warm climate. The oceans were not frozen solid. The simplest way to fix that contradiction is with greenhouse gases. Early Earth's atmosphere probably had much higher CO2 levels than today, and possibly more methane from early microbes. Those gases trapped more heat and compensated for the weaker sunlight. As the sun brightened over billions of years, weathering and biological activity likely pulled CO2 down. The thermostat adjusted. At each stage, the mix of sunlight, gases, continents, and life had to land inside a range where liquid water stayed on the surface. This is not automatic. It's a balancing act involving mantle convection, plate motions, continental positions, volcanic outgassing, biology, and radiation from the star. Change any one piece too much or too fast and you fall off the tightrope, into deep freeze or into runaway hothouse. Climate physics also tells you that one planet, one climate is too simple. For a given incoming energy from the star, an Earth-like world can sit in more than one stable state. You can have a snowball state with ice reaching near the equator, a temperate state with small ice caps, or a hothouse state with little or no permanent ice. Which one you get depends on ice coverage, greenhouse gas concentrations, cloud behavior, and atmospheric composition. Feedbacks are what make multiple states possible. Ice is bright, it reflects a lot of sunlight. If ice spreads toward lower latitudes, the planet reflects more light, cools more, and ice spreads further. That's a positive feedback toward a snowball. Water vapor is a greenhouse gas. If temperatures rise and more water evaporates, you trap more heat, which drives more evaporation. That's a positive feedback toward a hot, moist state. Clouds can go either way depending on altitude and type. When you cross certain thresholds, ice reaching lower latitudes, CO2, or water vapor reaching high levels, the feedbacks flip from stabilizing to amplifying. Once a planet tips into one of these runaway modes, it can stay there for a very long time. A snowball Earth can persist until volcanic CO2 builds up enough to break the ice. A hothouse like Venus can stay hot as long as CO2 remains high and no strong sink exists to remove it. The planet is still stable, just in a state that's terrible for complex surface life. The dangerous part is how small the pushes can be when you look over millions of years. You don't always need a giant asteroid or a Siberia-scale volcanic event to trigger big climate shifts. A small increase in volcanic CO2 outgassing sustained over a few million years, a slow change in the shape of a planet's orbit or its tilt due to gravitational tugs, or the gradual rearrangement of continents that opens or closes ocean circulation paths, each of these can nudge the system. Paleoclimate records from ice cores and ocean sediments show that even in the last few million years, when Earth was relatively stable, temperature and CO2 rose and fell significantly in rhythm, with subtle changes in Earth's orbit and tilt. Those are the Milankovitch cycles that drive the timing of ice ages. The actual shifts are big, about 5 to 6 degrees Celsius, 9 to 11 degrees Fahrenheit, globally between glacial and interglacial periods. That's from tiny, predictable orbital variations plus feedbacks in ice, oceans, and vegetation. On many exoplanets, the same size perturbations might be enough to overshoot. Their continents could be in different places, their oceans might be shallower or deeper, their atmospheres might start with more or less CO2 or water vapor. A slightly different configuration might mean that when ice starts to grow, it runs all the way to the equator instead of stopping. Or when greenhouse gases build up, the planet tips into a moist or runaway greenhouse instead of levelling off. In those systems, what looks like a small push on paper ends up being the trigger for a full climate flip. When scientists run planetary climate models across many scenarios, different star types, different orbits, different land-ocean layouts, they do not see Earth-like temperate as the default output. They see a zoo of outcomes: frozen worlds locked in ice, steam worlds with high-temperature atmospheres, and planets that jump back and forth between extreme glacial and extreme hothouse states. Or add in the real evolution of stars where luminosity rises over time and the available stable window narrows further. A long-lived moderate climate like Earth's, liquid water for billions of years, plate tectonics, recycling carbon, a greenhouse effect strong enough to prevent total freeze but weak enough to avoid runaway, starts to look like a very specific alignment. You need the right star, the right orbital history, the right internal heat flow, the right distribution of land and sea, and the right atmospheric starting conditions. Miss on any of those, and you still get a planet in the habitable zone by simple distance, but you don't get a world that stays friendly for complex life. So on paper, you can count billions of Earth-sized planets in habitable zones and say, the galaxy is full of potential Earths. But once you factor in climate physics, stellar evolution and feedbacks, it's more accurate to say, the galaxy is full of chances for planets to briefly pass through an Earth-like phase and then fall into a stable but dead state. Those are climatic dead Earths. Planets where the chemistry and geography never quite sync up for long enough, or get it right for a while and then lose it. They might have oceans for a few 100 million years, then freeze solid. They might start cool and moist, then drift into permanent hothouse. From far away, you just see a small planet with the wrong spectrum for a living, breathing biosphere. And even if a planet does manage to balance on that knife edge long enough for intelligence and technology to appear, there's still one more problem. What happens when a young civilization starts pushing on its own climate and life support systems as hard as it can? If advanced civilizations were common and long-lived, the sky should already show it. So far it doesn't. For decades, radio telescopes have scanned the sky for narrow-band, repeating signals that don't look like natural emission. They've found interesting blips, but nothing that holds up as a clear, artificial beacon. No steady, obvious hello that repeats on precise frequencies over years and from the same point in space. Infrared sky surveys look for stars or galaxies where a large fraction of the starlight is missing and replaced by smooth waste heat, which you'd expect if giant energy-collecting structures, Dyson-style swarms, were common. They don't see galaxies that look radically altered like that. When you look at exoplanet atmospheres today with space telescopes, your precision is limited, but good enough to see broad features: water vapour, carbon dioxide, maybe methane, sodium, or potassium in some cases. Those spectra fit natural explanations. You don't see sharp, isolated lines from strange industrial chemicals at concentrations that would scream technology. None of this proves there are zero civilizations. It does strongly suggest that galaxy-spanning, high-energy civilizations that modify stars and planets on huge scales are not all over the place. If they were, your instruments should have picked up at least a few obvious examples by now. On Earth, you can see why that kind of visibility might be rare just by looking at how young your own technological phase is and how fast it's pushing limits. In only a few centuries, global energy use has grown from almost nothing in planetary terms to many terawatts. CO2 emissions from burning fossil fuels have shot up, and material extraction has exploded. This is what a young technological species looks like. Exponential curves everywhere. Population, energy, data, built area, all bending upward hard. But physics does not allow exponential growth to continue forever on a finite planet. Even if you somehow removed greenhouse gases from the equation, waste heat from energy use alone eventually becomes a problem. Every joule of energy you use ends up as heat. If total energy use keeps doubling on short timescales, you eventually reach a point where the waste heat starts to noticeably warm the surface. Simple thermodynamic models, using realistic growth rates of a few % per year, show that you hit uncomfortable levels in a few thousand years. That is nothing compared to the lifetime of a star, which is billions of years. Right now, Earth is running a real-time test of this. CO2 levels in the atmosphere are higher than they've been for millions of years, and they're rising tens to hundreds of times faster than during natural glacial interglacial cycles. Ice cores give you direct samples of ocean air. Modern sensors track the rise year by year. Climate models predicted rapid warming from this, and observations show that warming happening. Global average temperatures up about 1 degree Celsius, around 2 degrees Fahrenheit, in just over a century, with more locked in. Any industrial civilization that uses stored chemical energy on a large scale, fossil carbon here, some other concentrated fuel elsewhere, will face this basic problem. You get a burst of cheap energy, you build infrastructure fast, and if you aren't careful, you destabilize the climate that your agriculture and cities depend on. The test is simple to state and hard to pass. Can you switch to long-term sustainable energy sources and manage your impacts before the biosphere you rely on starts to fail? If you fail that test, the result is more than inconvenience. You can push your own planet into a new climate state. Ocean circulation can change, ice sheets can shrink or grow in unfamiliar ways, key ecosystems can collapse. That can trigger a mass extinction that includes the civilization itself. From the outside, a million years later, all that remains is a thin layer in the rocks and a different mix of species, if anything complex survives at all. Climate is only one self-inflicted risk. Once a species knows enough physics to build nuclear weapons, it knows enough to destroy itself quickly. A global thermonuclear war would inject huge amounts of dust and smoke into the atmosphere, cut sunlight, and trigger a nuclear winter. That could hammer agriculture and lead to a large-scale die-off, even if the bombs didn't hit every region directly. As technology advances, more categories of systemic risk appear. Biotechnology makes it possible to engineer pathogens that can spread farther or kill more effectively than natural ones. nanotechnology raises the threat of uncontrolled self-replicating systems if designs go wrong. Advanced AI, if deployed without strong safeguards, could create new failure modes that don't map cleanly onto any past risks. On Earth, recorded history already contains multiple near misses with nuclear war and dangerous pathogens. Those are warnings about how narrow the safety margin is. On cosmic timescales, you can think of these as microfilters. Each year, the chance of a civilization wiping itself out might be small, but multiply that small risk over centuries or millennia of high technology activity, and the cumulative probability that something goes badly wrong rises toward 1. If most civilizations enter a phase of rapid growth, build powerful tools, and only a tiny fraction manage to stabilize before hitting a catastrophe, then very few will last long enough or grow big enough to be easy to see from other star systems. If that's the case, what would the losers actually look like through a telescope? During their active phase, a civilization might briefly load its atmosphere with strange molecules. On Earth, chlorofluorocarbons are an example, synthetic compounds with no strong natural source. Some of them have sharp absorption features in the mid-infrared. Seen from light years away, a planet with industrial levels of such gases would show spectral lines that don't fit normal geology or biology. You might also see rapid changes in greenhouse gases or in aerosols over centuries. In principle, a very advanced telescope could notice that an SOE O2 or methane content was changing orders of magnitude faster than any known natural process would allow, but those are short windows. Many industrial pollutants break down in decades or centuries. Others get buried in sediments, dissolve into oceans, or are broken apart by sunlight. Even CO2 spikes eventually get drawn down on 100,000-year timescales by weathering and sedimentation. If a civilization crashes, its technosignatures fade fast in cosmic terms. After a few million years, most of the direct atmospheric traces are gone. After tens of millions, plate tectonics and erosion start to recycle or hide surface structures. A future geologist on that world could still read the story in subtle isotopic ratios and odd mineral layers, but a distant observer with a telescope would just see a planet with an atmosphere shaped by new, simpler processes. Maybe the biosphere is weakened or dead. Maybe only microbes remain. In either case, there is no obvious radio noise, no strong industrial gases, no megastructures. That's a necrosignature, the indirect, decayed signal of a civilization that briefly existed and then vanished. It's not a bright, clear warning sign. It's the absence of ongoing activity and the presence of a few chemical scars that are hard to see unless you look very closely. If most civilizations burn fast and then go dark, the odds of catching one in its bright, noisy phase are low. Multiply that by the great filters you saw earlier, and it becomes understandable why your telescopes mostly see quiet planets. Many of them may not be untouched. They may just be long past the period when their technology was visible. The paradox is that the same tools you'd use to detect living worlds, sensitive spectroscopy, careful monitoring of atmospheres, are also the tools you'd use to detect dead ones. As those tools get better, you won't just be looking for thriving biospheres. You'll also be able to look for planets that clearly used to be better off than they are now, so the next step is to ask, with the instruments you're building, what can you actually see in a distant planet's air and light? And how would you tell a living Earth from a dead Earth that once had life, or even once had civilization? How do you actually tell if a distant planet is alive when all you see is a tiny dip in starlight or a faint pixel on a detector? That's the stage you're on right now, moving from guessing about life to trying to measure it directly. The main tool at the moment is transit spectroscopy. When a planet passes in front of its star, a thin ring of starlight filters through the planet's atmosphere before it reaches your telescope. Different gases absorb specific wavelengths. By comparing the star's spectrum when the planet is in front to when it's not, you can see which wavelengths get shaved off. That missing light tells you what's in the air. With current instruments, you can already detect broad features from molecules like water vapor, carbon dioxide, and in some cases methane in big hot exoplanet atmospheres. For small rocky planets, it's much harder, but you're finally getting close to being able to do the same thing. Sniff the air of a world roughly Earth-size. The big prize is a combination of gases that don't sit in chemical balance unless something is constantly rebuilding them. On Earth, oxygen and methane are like that. Oxygen is extremely reactive. It likes to bind to rocks and other elements. Methane gets broken apart by sunlight. Yet Earth's atmosphere has both. About 21% oxygen and small but steady traces of methane. That's because life keeps making them. Photosynthesis for oxygen, microbes and other sources for methane. If you saw a similar strong oxygen plus methane signal in the atmosphere of an Earth-like planet in the habitable zone with no obvious non-biological explanation, that would be a classic biosignature. It would say there is some ongoing process, very likely life, keeping the atmosphere away from simple chemical equilibrium. But drawing that line between life and no life is harder than it sounds, because geology and sunlight chemistry can fake you out. Volcanoes can release methane. Strong ultraviolet light from a star can split water and create oxygen under some conditions. Water rock reactions can also make hydrogen and methane. A planet around a small active red dwarf might build up oxygen in its atmosphere just from water loss and photochemistry, even if there's no biology. So astronomers are building detailed models to sort true biosignatures from false positives. They simulate many star types, planet sizes, orbits, and atmospheric mixes. They ask questions like, if you put a lifeless ocean world around a dim red star, how much oxygen can you make just from breaking water with UV? If you have a planet with a thin CO2 atmosphere and lots of volcanic activity, what methane levels do you get naturally? Where do the numbers land if there is no life? They also worry about false negatives, where life is there but you don't see its signature. A heavy cloud layer can block your view of the lower atmosphere. An ocean world with almost no land might not run a familiar carbon cycle. Early Earth had life for billions of years before it built up large amounts of oxygen. All this means the first claimed detection of life on an exoplanet will have to pass a brutal test. It won't be enough to say we see oxygen. You'll have to show that the whole atmospheric mix, given the star and planet, is best explained by biology, not by volcanism, photochemistry, or some weird but natural chemistry. That's the forward problem, proving a planet is alive. But there's also the backward problem, spotting planets that used to be alive and aren't anymore. A world that once had a thick oxygen atmosphere and surface oceans, then lost its water, should leave behind traces. When water gets broken apart by ultraviolet light, hydrogen escapes more easily than heavier isotopes like deuterium. Over time, that enriches the remaining water and any residual atmosphere in the heavy version. Venus is a good example. Its high deuterium to hydrogen ratio is a clue that it used to have much more water. On a distant exo-Earth that went down a similar path, you might see an atmosphere with very little water vapour, strong CO2, and isotopic signatures showing that the lighter hydrogen has been preferentially lost. You might also see an atmosphere with oxygen present, but with clear signs that it isn't being refreshed by biology. No methane, no nitrous oxide, and a very dry spectrum. Most of the oxygen could be locked into surface rocks, iron oxides and other minerals, as a fossil of a past wetter era. A planet that went through catastrophic warming and biomass collapse might look like a CO2-rich hot world with almost no biosignature gases left. You wouldn't just see a hot atmosphere, you'd see an atmosphere missing the tiny but important components that active biospheres tend to maintain. In other words, not just no strong enough signal, but a spectrum that suggests this world had water and lost it, or had a biosphere and then shut it down. Then there's the question of technology. Can you see direct fingerprints of industry, even briefly? Some industrial gases have no easy natural production route. On Earth, certain fluorocarbons and related compounds fall into that category. They are used in refrigeration, manufacturing, and other industrial processes, and they show very specific absorption features in the mid-infrared. In principle, a telescope with enough sensitivity could pick out those fingerprints in a distant planet's spectrum if the gas concentrations were high enough. That would be a technosignature, Not just life, but technology. A planet with chlorofluorocarbon levels like late 20th century Earth, for example, would stand out as unnatural. The catch is that most of these compounds are short-lived in atmospheres. They break down under ultraviolet radiation, get destroyed by chemical reactions, or are otherwise removed on timescales of decades to centuries. Even more stable industrial gases won't last more than thousands of years without a continuous source. If a civilization rises, pollutes its atmosphere with such gases for a while, and then collapses or reforms and stops producing them, the spectral signals fade quickly. The window when you could catch that planet in its industrial spike is tiny compared to the billions of years of its existence. It's like trying to take a random snapshot of a city's fireworks show and expecting to catch the exact second of maximum brightness. This is why the next generation of telescopes matters so much. Right now, your best tools, like the James Webb Space Telescope, are just beginning to probe the atmospheres of small exoplanets. They can already detect some broad features in favourable cases, but upcoming instruments will push much further. In space, future observatories with ultra-cold infrared detectors and larger mirrors will be able to separate the light from small, cool planets from the glare of their stars more cleanly. On the ground, extremely large telescopes with mirrors 30 to 40 meters across, about 100 to 130 feet, will collect far more light and use advanced optics to sharpen the view. With that combination, you'll be able to get detailed spectra of a wider range of planets, not just hot gas giants and a few super-Earths, but more true Earth-sized worlds in habitable zones around nearby stars. You'll see which ones have water vapor, which ones have CO2-heavy dry atmospheres, which ones show hints of oxygen and methane together, and which ones look stripped or chemically odd. Over the coming decades, that moves you from statistical hints to actual case files. You'll have planets where the data point to active biospheres, planets that look marginal, barely hanging on to habitability, and planets that clearly fit dead Earth categories, dry, overheated, frozen, or with atmospheres that scream runaway past or lost oceans. At that point, you're not just hunting for living Earths, you're doing planetary autopsies across light years, reading cause of death from spectra. Each dead Earth you identify tightens the noose on the great filters you've been talking about. Each living Earth tells you how narrow the path really is, and once you start sorting planets into safe for a long time and doomed zones, the next question becomes, how much of the galaxy is even capable of supporting those long-term survivors in the first place? You've been thinking about habitable zones as narrow bands around stars, but the harder truth is that whole regions of the galaxy are bad neighbourhoods for long-term life, where your star orbits matters almost as much as what kind of planet you stand on. Astronomers use the term Galactic Habitable Zone for this. Near the centre of the Milky Way, within a few thousand light-years of the core, space is crowded. Star density is high, supernovas are more frequent, radiation levels are higher, and the central black hole is active over long stretches. Gravity is messy, close encounters between stars are more likely. That's bad for stable planetary orbits and bad for fragile atmospheres. Far out in the disk, tens of thousands of light-years from the centre, you have the opposite problem. Space gets quieter, but also poorer. The gas there has fewer heavy elements. The carbon, oxygen, silicon, iron, and so on will be that you need to build rocky planets. Astronomers call everything heavier than helium metals, and stars in the outer galaxy are, on average, metal poor. Fewer metals generally means fewer solid cores, which means you might get fewer Earth-like worlds to start with. Earth and the Sun sit somewhere between these extremes, around 26,000 light-years from the galactic centre. Not in the central chaos, not way out in the thin metal-poor outskirts. Once again, you're in a middle band that happens to work. The metallicity story is straightforward but important. The early Milky Way was mostly hydrogen and helium left over from the Big Bang. The first generations of stars had almost no heavy elements. They lived, exploded as supernovas, and spread heavier atoms into space. Each generation enriched the gas a bit more. Over billions of years, This recycling built up regions with enough metals to form solid rocky planets in large numbers. Observations today show a clear pattern. Stars with higher metallicity are more likely to host giant planets, and by extension they formed from disks with a lot of solid material. Stars that formed very early, when the galaxy was young and metal poor, often have very low, heavy element content. Many of those systems probably never had enough raw material to assemble Earth-mass rocky planets at all, or only formed small marginal ones. That means most of the potentially habitable planets, Earth-size, with enough rock and water, are not around the oldest stars in the galaxy. They formed later, after many cycles of star birth and death. Huge swathes of the galaxy, especially in the outer parts and in some old populations closer in, might be quietly sterile at the level of solid planets. The gas there simply never got rich enough in heavy elements to build a lot of Earth-like worlds. Now combine that with the radiation hazard you saw earlier. When you model the rate of nearby supernovas as a function of distance from the galactic centre, the curve jumps up sharply as you move inward. The inner disk and bulge pack are more massive stars per cubic light year. Those stars die fast and violently. Some types of gamma-ray bursts are also more likely in regions with active star formation and certain metallicity conditions, which again bias them toward inner and denser parts of galaxies. Put a planetary system in those zones and over a few billion years, it will see more close supernovas and a higher chance of being inside the beam of a GRB. That doesn't mean instant death every time, it does mean more frequent hits to the ozone layer, more climate shocks, and a higher chance of full-surface sterilization events. On the far outer edge of the galaxy, the situation flips. Supernovas are rarer, so radiation risk is lower, but metallicity is low. You trade physical safety for a shortage of building material. Somewhere between these two extremes lies a band where you have enough heavy elements to form rocky planets, but not so much crowding and star-forming chaos that you're constantly being blasted. The Sun appears to be in that band, but even inside this galactic habitable zone, the story isn't over, because stars don't sit still in nice clean rings. The Sun orbits the galactic centre roughly once every 220 to 250 million years at a speed of about 220 kilometers per second, roughly 490,000 miles per hour. As it goes, it doesn't trace a perfect circle in a flat plane. It bobbles up and down through the galactic disk and drifts in and out of spiral arms. Spiral arms are density waves, regions where gas is compressed, stars form, and massive short-lived stars light up and explode. Passing through a spiral arm means moving through a region with more young, massive stars and more supernovas. Some studies have suggested that certain mass extinctions on Earth might line up in time, very roughly, with spiral arm crossings or other orbital features. That link is still debated, but the basic point stands. Your star's path through the galaxy changes its exposure to dangerous vents. If the Sun's orbit were a little closer to the centre, or more tightly linked to the arms, Earth might have spent more time in high-risk zones. That could mean more nearby supernovas, more strong radiation hits, and a much rougher ride for complex surface life. On the other hand, if the Sun formed farther out in a metal-poor region, Earth might not exist at all, or might be a smaller, drier world with less chance to maintain plate tectonics in a magnetic field. Scale this up to all stars. Many Sun-like stars will have orbits that carry them into spiral arms more often, or keep them closer to the galactic centre. Others will live in thin outer regions with few metals. A smaller fraction will trace out safe, relatively circular orbits in the mid-disk, with moderate metallicity, away from the worst of the explosions. When you combine all these factors, metallicity, radiation environment, and orbital history, you can sketch a galactic habitable zone as a relatively narrow ring in radius and a thin slice in thickness through the disk. It's not a razor-sharp edge, but it's definitely not the whole galaxy is equally good. Inside that region, some stars will still be bad bets because they formed in dense clusters, had close stellar neighbours, or migrated into risky zones. Others will be better bets because they spent most of their time in quieter space. Each of those filters cuts down your numbers. Start with maybe a few 100 billion stars in the Milky Way. Knock out the ones that formed with almost no metals, fewer rocky planets. Remove the ones too close to the centre or locked in violent starburst regions. Too many sterilizing events. Subtract systems with chaotic orbital histories that drag them through spiral arms and dense clusters over and over. What you're left with is a minority of stars in a particular band, on particular kinds of orbits, with the right raw materials and a decent safety record. Even inside that reduced set, you still have to ask whether the individual planetary systems got the right mix of planet sizes, orbits, and internal structures. Most won't. A few will. Earth seems to be one of them. That alone makes it unusual. So the galaxy isn't just full of random Earth scattered everywhere. It's full of regions where Earth-like planets are unlikely to form, regions where they form and get blasted, and a relatively small region where they have a chance to last. Most worlds outside that strip either never had the right starting ingredients or had them, and lost their shot early under heavy fire. But even inside that galactic safe zone, most stars are not Sun-like. The majority are smaller, cooler red dwarfs. They bring their own set of problems: tight habitable zones, intense flares, and tidal locking. If you're counting future Earths, they dominate the numbers. If you're counting long-term safe Earths, they might be some of the biggest traps. So the next step is to look at those red dwarfs and ask a blunt question. Are they the universe's main hope for life? Or are they factories for yet another class of dead Earths? You might think Sun-like stars are the main stage for life, but most stars in the Milky Way don't look like the Sun at all. They're smaller, cooler red dwarfs, what astronomers call M-type stars. These stars have masses from about 10 to 50% of the Sun and shine much more weakly. Because they burn hydrogen so slowly, they can live for tens to hundreds of billions of years. That's far longer than the current age of the universe, about 13.8 billion years. If you're counting star lifetimes, red dwarfs look like perfect candidates for long-term habitability. There's also no shortage of them. Roughly 3 out of every 4 stars in the galaxy are red dwarfs. Surveys show they are packed with planets. Many of those planets are roughly Earth-sized, not giant gas worlds. So if you just look at raw numbers, how many stars, how many small rocky planets, how many habitable zone orbits, red dwarf systems completely dominate the statistics. On paper, most of the potential homes for life in the Milky Way orbit these faint red stars. So where's the catch? Because red dwarfs are so dim, their habitable zones sit very close in. Instead of orbiting at around 150 million kilometers like Earth does, a planet in the habitable zone of a cool red dwarf might orbit at 5 to 20 million kilometers, only a few % of Earth's distance from the Sun. At those distances, the orbital period is short. A year could be just a few days to a few weeks long. That tight geometry is great for detection. Planets close to small stars block a bigger fraction of their light when they transit, so the dip is easier to see, and the star wobbles more visibly in response to a close-in planet's gravity. That's why many of the first Earth-sized planets in or near habitable zones, like the TRAPPIST-1 system, have been found around red dwarfs. They check all the basic boxes, small, rocky, in the right temperature band. For a while they looked like ideal targets. The problem is that being in the habitable zone by distance doesn't guarantee what's happening at the surface. Red dwarfs, especially when they're young, are extremely active. They produce powerful stellar flares and coronal mass ejections. These outbursts flash intense X-rays and ultraviolet radiation and hurl streams of energetic particles into space. Observations show that many red dwarfs flare far more often and more violently than the Sun does. For planets tucked in close, that radiation hit is much stronger than what Earth gets. If a planet in that region has a weak magnetic field or none at all, those flares and particle storms can slam its upper atmosphere directly. Over time, that drives atmospheric escape. Light molecules get knocked to speeds above escape velocity and drift off into space. Even with a magnetic field, repeated huge flares can eat away at the air, especially when the star is in its most active phase early in its life. You can plug real flare energies and particle fluxes into atmospheric escape models. The results are not friendly. Many close-in Earth-sized planets around active red dwarfs end up with very thin atmospheres, or they lose their atmospheres entirely over hundreds of millions to a few billion years. A habitable zone orbit in these cases just means where liquid water could exist if there were an atmosphere. It says nothing about whether an atmosphere is actually still there, and even if the planet manages to hold on to thick air, there's another issue: how that air and surface behave under constant one-sided heating. Planets this close to their stars are very likely tidally locked. That means one side always faces the star, permanent day, and that other side always faces away, permanent night, the same way the moon always shows one face to Earth. On a tidally locked world, the day side gets constant energy. The night side gets almost none. Climate simulations show that in principle, you can still get a broadly habitable planet in that setup, if certain conditions are met. A thick atmosphere and possibly oceans can move heat from the day side to the night side through winds and currents. That can smooth out the temperature difference and create a wide area, especially around the terminator line between day and night, where temperatures stay in a comfortable range for liquid water. But that balance is delicate. If the atmosphere is too thin, heat can't move efficiently. The day side may become extremely hot while the night side turns into a deep freeze. Volatiles like water and carbon dioxide can freeze out on the night side or at the poles as permanent ice, slowly draining the atmosphere. If greenhouse gases are too strong, the day side can push toward a runaway greenhouse while the night side still sits in shadow. You can get extreme winds, huge storms pinned near the substellar point, and weird cloud patterns that block or trap heat in unstable ways. Small changes in atmospheric composition or total mass can flip a tidally locked planet from somewhat stable to runaway state, or to collapsed atmosphere on the night side. That's not a forgiving setup for long-term complex surface life. It might allow narrow strips or patches to stay habitable, but the margin is thin. So now you have three competing facts about red dwarf systems. 1. There are many of them, and they live an extremely long time. 2. They have lots of small rocky planets in or near tight habitable zones. 3. The inner regions around these stars are blasted by high energy flares early on, and any surviving planets are probably tidally locked with tricky climate dynamics. The irony is sharp. Red dwarfs could, in theory, offer windows for life that last far longer than a sun-like star can provide, tens or hundreds of billions of years instead of 10 billion. But their early violence and their close inhabitable zones may wipe out or severely damage many of the promising planets before life has a real chance to get beyond simple, shielded microbes. You might still have niches, underground aquifers, deep oceans, or atmospheres thick enough and magnetospheres strong enough to ride out the early storms. Microbial life in protected environments could be common, but surface biospheres rich enough to build forests, animals, and technology are a much harder ask. To your telescopes, a tidally locked atmosphere-stripped rock the size of Earth, orbiting a red dwarf at a few million kilometers, just looks like another small planet. Its brief habitable phase, if it had one at all, would be invisible. Given how common red dwarfs are, the universe could be packed with these false-dawn Earths, worlds that all looked great on paper, maybe even had liquid water for a while, then slipped quietly into permanent, simple or lifeless states. They inflate the count of Earth-sized planets in the habitable zone, but not the count of long-term, stable, complex biospheres. And that leads to another uncomfortable angle on the Fermi Paradox. Even if you dodge red dwarf traps and find a sun-like star in a safe galactic zone with a genuinely good Earth, timing still matters. The universe itself is on a schedule. Most of the planets that could ever exist haven't formed yet, so the next question is this: not where are they, Sam, but when should we actually expect them? If you're living this early in cosmic history, maybe the silence says as much about timing as it does about death. The universe is not that old compared to how long stars can live. That matters for when you should expect other civilizations to show up. Cosmology says the universe is about 13.8 billion years old. Stars like the Sun live around 10 billion years. Small red dwarfs can burn for hundreds of billions to trillions of years. When people model star formation and planet formation forward in time, using what we know about how gas clouds collapse and how disks build planets, one result stands out. Most of the Earth-like planets that will ever exist have not been born yet. Heavy elements keep building up as more generations of stars live and die. There's still plenty of gas left in galaxies to form new stars. And red dwarfs that form now will keep their habitable zones for time spans far longer than the age of the universe so far. Statistically, that means the peak of habitable planet numbers lies in the future. You're living near the leading edge of the habitable planet curve, not in the middle of it. If that's true, then being early can explain part of the silence. If evolution to intelligent technological life usually takes several billion years on a stable world, and most habitable planets will form later, then most potential civilizations are also in the future, not the past. On average, you wouldn't expect a sky full of old advanced neighbours yet. You'd expect a mostly quiet universe that is only just starting to turn on a few lights, but that argument doesn't get you all the way out of the paradox. There are stars in the Milky Way that are older than the Sun by several billion years. Some of them have decent metallicity, meaning they had enough heavy elements to build rocky planets early. Those systems had time to form Earth-like planets, cool them, run biology, and evolve intelligence long before Earth formed 4.5 billion years ago. Even if most habitable planets are in the future, a non-trivial number are in the past. The total count of past chances is smaller than the total future chances, but it isn't zero. Yet you still don't see clear signs of old galaxy-spanning civilizations. That implies something else is cutting down the number of survivors, not just timing. Either the early environments were much harsher than you thought, or the filters you've been talking about, geological, biological, technological, are strong enough that even with billions of years head start, almost nobody makes it. Some ideas push in the opposite direction. They assume that once a civilization does get through those filters and becomes truly expansionist, it changes everything around it. These grabby alien models say that a civilization which decides to spread and can travel at, say 10% of light speed 0.1 c, will rapidly expand outwards in all directions, colonizing or transforming new systems as it goes. Over tens or hundreds of millions of years, that expansion front would carve out a visible bubble in the galaxy. Star formation patterns, starlight spectra, or waste heat signatures could all end up looking very different inside that bubble compared to outside. If civilizations like that were common and started early, you wouldn't have to detect their radio chatter to know they exist. You'd see large regions of the sky where the energy distribution of stars looked off, or where whole swathes of a galaxy appeared dimmer in normal light and brighter in infrared from all the waste heat. You don't see that, either, in the Milky Way or in other galaxies you can resolve. That alone says that if expansionist, high-impact civilizations exist, they are not common or they started only very recently, or they are expanding slower and in ways that are hard to detect. That pushes the pressure back onto the idea that something is stopping most biospheres long before they become grabby on galactic scales. There's another uncomfortable angle. The biggest great filter might still be ahead of you, not behind. Maybe getting from a habitable planet to microbes is relatively easy. Maybe even getting from microbes to multicellular life and then to basic intelligence isn't as hard as it looks, given enough time in a stable window. But going from a young industrial civilization, like the one you live in now, to a truly stable high-technology society that lasts for hundreds of thousands or millions of years could be the step that almost nobody clears. Think about the timescales. Earth has only had radio for about a century, heavy industry for a couple of centuries, and nuclear weapons for less than 100 years. In that short interval, you already see global environmental change, world wars, near misses with nuclear disaster, and rapid, poorly understood shifts in technology. If the average technological civilization spends only a few thousand years in this volatile high-risk phase before stabilizing or collapsing, that's still basically zero on a 10 billion year clock. If most of them don't stabilize, they add almost nothing to the odds of two such civilizations overlapping in space and time and noticing each other. You could have many worlds that pass through radio age for a few thousand years and then go silent forever. The chance that two of those are within a few hundred light years of each other and active at the same time is small, so you end up with several layers at once. Most habitable planets are in the future, so the universe is naturally quiet now. Among the ones that formed early, many were in harsher environments or had less favourable setups, and among the tiny fraction that did get to technology, many may have burned out quickly. When you stack those probabilities, a quiet sky looks less surprising. Now put all these threads together. You know that Earth-like planets are common in size and orbit. You know from Venus, Mars and exoplanet studies that habitable conditions are fragile and often temporary. You know from Earth's own history that complex life took billions of years and nearly died multiple times. You know there are galaxy-scale hazards, supernovas, gamma-ray bursts, and that safe regions in the galaxy are limited. You know red dwarfs dominate the star count but are risk-heavy for surface life. You see no clear signs of grabby, galaxy-shaping civilizations in the data. And theoretical work says most future Earth-class planets haven't formed yet. The simplest reading is not cheerful. You might indeed be early in cosmic terms, sitting before the big wave of future habitable planets, but you're also sitting on top of a stack of filters and hazards that most worlds probably fail. The universe will likely produce immense numbers of Earth-class planets over the next tens of billions of years. Most of those planets will never host complex life. Many that do will never reach intelligence. Many that reach intelligence will fail the technological endurance test. A small fraction will get as far as you have. A much smaller fraction will last long enough and grow big enough to be obvious. The fact that you are here now, looking out with real instruments and seeing only natural light and noise, is not neutral. It's data. It suggests that so far, dead Earths are the standard outcome. Living, technological Earths are rare and short-lived. That leaves one last question hanging over everything you've seen. If the default outcome is that planets like this end up as silent rocks, what are you going to do with the one that hasn't died yet? By this point, the numbers are hard to dodge. Data from Kepler, TESS and ground surveys say Earth-size, roughly temperate planets are common. Venus and Mars show that even in one small solar system, habitable worlds can flip to dead states in very different ways. Earth's rocks show that complex life here has been smashed over and over by impacts, volcanoes and climate swings. Stellar physics and galactic models say the Milky Way is full of extra hazards. Supernovas, gamma-ray bursts, flare stars, chaotic orbits. Searches for techno-signatures say that big, loud, long-lived civilizations are either rare or not in your neighborhood. Stack that up. You're looking at a universe that is very good at making Earth-like planets, billions of them in this galaxy alone, and just as good at destroying or degrading them. Most Earths form, most Earths die, some never light up at all. That's the background setting you actually live in. Now zoom in on your specific case. On a random Earth-class planet, step through the probabilities with everything you've seen. First, the planet has to form in the right place in the galaxy, with enough heavy elements at the right distance from its star, with the right mass and spin. Many never clear that first hurdle. Among the ones that do, life has to start. On Earth it happened quickly, but that doesn't prove it's guaranteed. On a lot of worlds, the chemistry might stall out. If life starts, getting past microbes to complex multicellular organisms takes billions of years and probably depends on rare events and stable climate windows. Many planets will freeze, boil, lose their atmospheres, or take repeated hits from asteroids or stellar radiation before they get that far. If complex life appears, it has to ride out mass extinctions and climate whiplash long enough for intelligence to evolve. If intelligence appears, it has to build technology and then somehow keep its own tools from destabilizing its environment or triggering self-destruction. You live on a world that so far has threaded all of those needles. It formed with the right metals, kept a thick atmosphere, ran plate tectonics in a magnetic field for billions of years, started life early, made it through at least 5 major mass extinctions, and then produced a technological species right before its long-term habitable window starts to narrow. Statistically, that is not the normal outcome. It's the tail sort of the distribution. That makes you the statistical freak, not the default case. On most habitable planets, the chain probably breaks early, no life or microbes forever. On many that get complex life, something like the Permian mass extinction or a snowball Earth analogue might be terminal instead of temporary. On planets that get intelligence, the odds are high that nuclear weapons, climate change, engineered pathogens, or other high-risk technologies show up before systems and cultures are stable enough to handle them over thousands of years. From orbit a million years later, almost all of those worlds look the same. Quiet air, natural spectra, maybe odd rocks, no obvious technology. So what do you do with that? One reaction is to shrug and say that if the universe kills most Earths, then nothing you do matters. That reaction doesn't change the physics. It also doesn't help you stay out of the dead Earth pile. The other reaction is more concrete. If conscious technological life is rare, then keeping it going and spreading it might actually be one of the very few things that changes the long-term story of the universe in a measurable way. The planet doesn't care. The sun doesn't care. The galaxy doesn't care. There's no built-in safety net. But you have instruments that can read ice cores and exoplanet spectra, simulations that can predict runoff from a volcano or a 10-kilometer impactor, and communications that move around the world at near light speed. You're not stuck guessing which filters exist. You can see them coming. In practical terms, that means treating Earth's life support system as the core hardware of your entire project, not as scenery. The same radiative transfer tools used to study distant atmospheres can tell you exactly what adding another 100 parts per million of CO2 does here. The same orbital mechanics used to simulate exoplanet climates can model how a slightly different tilt would affect ice sheets and sea levels. Ignoring those numbers isn't neutral. It's actively walking into the same traps that likely killed other Earths. Reducing your own filter means making it harder for any single shock to end everything. That can be very concrete. Track and deflect near-Earth asteroids before they hit at tens of kilometers per second and release gigaton-level energies. Harden infrastructure against solar storms and regional disasters. Cut the probability of full-scale nuclear exchange from low but real toward effectively zero. Shift energy systems away from fuels that dump long-lived greenhouse gases into the atmosphere faster than natural sinks can handle. Design AI, biotech, and other powerful tools with containment and fail-safes baked in, not as afterthoughts. Every step like that slightly lowers the chance that Earth becomes another silent rock with a thin, chemical scar where a modern civilization used to be. None of it makes you immortal. It just moves you a little further away from the edge. There's another layer, not just surviving on one planet, but reducing how much any one planet matters. If you accept that single-planet civilizations are fragile, then spreading out stops being a luxury project and starts looking like risk management. A species that builds permanent bases on the Moon and Mars, then on asteroids and outer system moons, is harder to wipe out with one impact, one supervolcano, or one pandemic. A civilization that can reach other stars at even a small fraction of light speed, tens of thousands of kilometers per second instead of a few kilometers per second, is no longer tied to the lifetime and quirks of one sun. The same skills needed to read dead Earth spectra, understanding atmospheres, climates, radiation environments, become tools for choosing where to go. You can pick star types and orbits that are safer over billions of years. You can spot red dwarf systems that are stripped and hostile, and skip them. You can recognize young systems full of debris where 1 kilometer impactors are still common, and avoid those too, whether this guarantees that your species becomes one of the rare grabby civilizations that change galaxies. It does something simpler. It raises your odds of not joining the giant background set of failed experiments. It extends the time window in which anyone is around to make telescopes, ask questions, and see what other worlds did. Right now, though, all of that is still potential. In reality, there is one known technological civilization on one known planet at one small distance from one ordinary star. Around you is a sky that, based on everything you've seen, is probably full of dead or never awakened Earths. Some boiled, some froze, some were sterilized from space, some may have burned themselves out with their own tools. None of them are talking to you. So the real question hanging over all of this is not where is everybody. You've seen plenty of reasons why almost everybody is gone or never started. The real question is narrower and sharper. Given everything you now know about how planets live and die, are you going to treat Earth as just another experiment that runs until it fails, or as the starting point for something that finally breaks the pattern? This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.